The atoms of all radioactive nuclides steadily decay into simpler atoms as they release radiation. Each atom of a radioactive species has a certain probability of undergoing decay within a window of time. This window of time is called half-life, which is the amount of time required for 1/2 the radioactive atoms to decay. For example, given this sample of 100 radioactive atoms, after one half-life period, half of the radioactive atoms decay into simpler atoms represented by the black circles. So my sample contains only 1/2 of the original radioactive atoms remaining. After a second half-life period, half the radioactive atoms decay, leaving 1/4 of the original sample. After a third half-life period passes, half the radioactive atoms decay, leaving 1/8 of the original sample, and so on, as shown in the next few slides. As shown on Regents Reference Table N, different radioactive nuclei have different characteristic half-lives, and for our purpose, the half-life is a constant value, unaffected by the amount of the sample, the temperature, the pressure, or the form of the radioisotope. There are a variety of ways to solve a half-life problem. You can just think it through, or you can use the mathematical equation shown here, where m sub f equals the mass of the radioactive nuclide remaining. M sub I represents the original mass of the radioactive nuclei. Capital T represents the total time that elapsed, and lowercase t represents the half-life of the radioactive nuclide. I will demonstrate a few methods on the next few slides. Example 1. You have 400 milligrams of a radioisotope with a half-life of 5 minutes. How much will be left after 30 minutes? So let's just think it through. I know that for every one half-life period that passes by, half of the radioisotope will decay. So if I can determine the number of half-life periods that have gone by, I then could keep dividing by 1/2 until I reach the number of half-lives that have gone by. So to determine the number of half-lives that have passed, we're going to take a total of 30 minutes divided by 5 minutes to get 6 half-life periods passed. Now I'm going to build a table that will cover my 6 half-life periods that have passed, starting at time 0 up to 6 half-lives have gone by. Now at time 0, my original sample is 400 milligrams. After 1 half-life goes by, 200 milligrams will remain. After 2 half-life periods go by, 100 milligrams will remain. After 3 half-lives go by, 50 milligrams will remain. After 4 half-lives that go by, 25 milligrams will remain. After the 5th half-life pass, 12.5 milligrams will remain. And finally, at the 6th half-life period passed, only 6.25 milligrams of the original sample will be left. Now another way to solve this is to use the mathematical equation. My original mass is 400 milligrams times 1/2 to 30 divided by 5. And I'm going to solve 30 divided by 5 first to get the number of half-life periods that have passed by. So 400 times 1/2 to the 6th power. Solving 1/2 to the 6th power, I get 400 times the fraction 1 over 64. Multiplying 400 times the fraction, I'll end up with 6.25 milligrams remains for my final mass. Example 2. How many half-lives have passed if 255 grams of cobalt-60 remain from a sample of 8,160 grams? Now I'm trying to find out how many half-life periods go by. And I know that for every half-life period that goes by, half of the sample will decay. So I'm going to build my table, and I don't know how many half-life periods have gone by, so I'm just going to build it from 0 to 6 half-lives have passed. Starting at time 0, I have 8,160 grams. After one half-life period, 4,080 grams will remain. After the second half-life period, 2,040 grams will remain. After a third half-life period has passed, 1,020 grams remains. After 4 half-life periods passed, 510 grams remains. After 5 half-life periods have gone by, 255 grams remain unchanged. So that tells me that 5 half-life periods have passed. Now, using the mathematical equation, we can set up our math problem by saying 255 grams is my final mass. 8,160 is my initial mass, times 1/2 to the x, which x represents the number of half-lives that have passed. So first divide by 8,160, and then we're going to take the log of each side to get the x out of the exponent. So I'll take the log of 0.03125 equals x comes in front of the log, so it's x times the log of 1/2. Now I'm going to divide the log to solve for x, so that I have the log of 0.03125 divided by the log of 1/2, which gives me 5 half-life periods have passed by. Example 3. Suppose you have a sample containing 400 nuclei of a radioisotope. If only 25 nuclei remain after 1 hour, what is the half-life of the isotope? So let me think it through. I need to determine how many half-life periods have passed. So I'm going to use my table, and I'm going to build it from 0 to 6 again because I don't know how many half-life periods have gone by. I'm going to start with my 400 nuclei at time 0. After 1 half-life goes by, 200 nuclei remain unchanged. After the second half-life goes by, 100 nuclei remain. After 3 half-lives go by, 50 nuclei remain. After the fourth half-life goes by, 25 nuclei remain, which is the number I was looking for. So I know that 4 half-life periods have passed in 1 hour. So, taking my total time divided by the half-life, which is represented by x, will equal 4 half-life periods, so that each half-life period will be 15 minutes. Now, using the equation to solve this problem, we're going to set it up so that we have 25 nuclei as my final mass and 400 nuclei as my original mass times 1/2, and then the total time is 60 divided by x, which is my half-life. So the first thing I'm going to do is divide each side by 400. Now, to solve this and to get the x out of the exponent, we're going to take the log of each side, so that we have the log of 0.0625 equals, bringing the exponent in front of the log so that it's 60 divided by x times the log of 1/2. I'm going to divide each side by the log of 1/2 so that I have 60 divided by x equals the log of 0.0625 divided by the log of 0.500. Solving, I get 60 divided by x equals 4. 60 equals 4x, and x equals 15 minutes, so that each half-life period is 15 minutes long. On the next slide are 3 half-life problems. Pause this video and solve the 3 half-life problems. After solving the problems, check your answers on the following slide by unpausing the video.